All right, we're going to go through and just do some examples here of working with complex roots to quadratics. So in the first example, suppose I say that 0 is n squared minus 3n plus 4. It's not clear immediately how to factor that, so I'm not going to mess around. I'm just going to use the quadratic equation. So b is negative 3, so negative a negative 3 plus or minus b squared, or minus 3 squared, minus 4 times 4, and a is 1, all over 2 times 1. So that becomes 3 plus or minus 9 minus 16 over 2. So that's 3 halves plus or minus 1 half, and then that's going to be what? Negative 7. So if I bring out that negative 1, I'm going to have an I. This becomes square root of 7 over 2. So that means if I have x of t is equal to c1 e to the z1t plus c2 e to the z2t, it's going to be e to the 3 halves t, so that's my d. This is this thing we call d, and this is my omega. This is all going to be times k1 cosine square root of 7 over 2t plus k2 sine of square root of 7 over 2t. So immediately, once you saw that the roots look like 3 halves plus or minus I square root of 7 over 2, you should immediately recognize there's going to be oscillations because there's an imaginary part. It's going to grow like e to the 3 halves t. And for the period, we're going to have, so in this case, omega equals square root of 7 over 2. So the omega times the period equals 2 pi. So the period is going to be 4 pi over square root of 7. Okay. Let's do another example. So in this example, suppose we have 0 equals n squared plus 3n plus 8. I don't see how to factor that, so n is going to be what? Minus 3 plus or minus 3 squared minus 4 times 8 times 1 over 2 times 1. So my a is 1. So minus 3 plus or minus 3 squared is 9. 4 times 8 times 1 is 32. I have 2 in the denominator. So I'm going to have minus 3 halves plus 1 half. So the 9 minus 32 is going to be what? 23. Gotta be careful, it's negative 23. So I'm going to have minus 3 halves plus I. So if I factor out the square root of negative 1, that becomes an I times 1 half square root of 23. It's complex. Right now, you should immediately look at this and see that we're going to have decay. And the amplitude is going to decay like this. It's going to oscillate. And for the period, the omega is 1 half square root of 23t. Or sorry, omega is 1 half square root of 23 times the period should be 2 pi. So the period is going to be 4 pi over the square root of 23. Okay. Let's do another example. Suppose we have a system and we're going to deal with that quadratic equation. And suppose we don't know what b is. So, and remember, b is the friction term. So what does this mean? This means then that if I go through and find the value for n, I'm going to have minus b plus or minus square root of b squared minus 4 times 5 times 1 over 2a, but a is 1. So I have minus b plus or minus b squared minus 20 all over 2. Okay. What does this mean? This means that if b squared minus 20 is greater than 0, then I'm going to have b squared greater than 20. And now, so this I got to be careful about. B could be positive or negative, right? If I take the square root of this, b could be less than negative square root of 20, or b could be greater than square root of 20. This is often, in physical systems, this is the friction term. So to be physically relevant, we need b greater than 0, which means this is going to be our choice. Okay. This is mathematically fine, but physically it's not good. So this means that if we have b greater than 20, square root of 20, we're going to have two distinct roots, and we're going to have decay. All right, so now, what's the other thing? Well, if we have b squared minus 20 equals 0, or b equal to plus or minus square root of 20, again, we want b to be physically relevant, so we'd want the positive. In this case, now we're going to have repeated roots. Okay. And then the final situation is b squared minus 20 is less than 0. So let's rewrite our equation for n. N is minus b plus or minus b squared minus 20 over 2. And we're going to assume that b is, let's be careful here. We have b squared minus 20 is less than 0. So b squared is less than 20. What does that mean? So if I look at this b squared minus 20, it's going to be 0 at square root of 20 and minus square root of 20. And it's going to be negative between negative square root of 20 and square root of 20. We're not going to worry, again, about this case because it's not physical. Our primary concern is what happens when b is non-negative, so it goes from 0 to 20. So let's focus on this case where b is between 0 and square root of 20. In this case, b squared minus 20 is negative, so I need to factor out a negative. So instead of b squared minus 20, I can think of it as 20 minus b squared, quantity negative. Now 20 minus b squared is positive. So I can factor out that square root of negative 1. And write this as minus b over 2 plus or minus I times 1/2 square root of 20 minus b squared. Okay. Now everything, as long as b is between 0 and square root of 20, that's my real part, that's my imaginary part. And notice, since b is positive, this whole thing is negative, so I'm going to get exponential decay, which makes physical sense. And I'm going to see oscillations with my omega now is 1/2 times the square root of 20 minus b squared. Okay. So what this says now is that I'm going to get decay like e to the minus b over 2t. And I'm going to have oscillations where my omega times the period is 2 pi. So my period now is going to be 4 pi over the square root of 20 minus b squared. Or, and I could be very careful, I could have a situation where I ask you to find b. And suppose I want you to find b so that the system decays and it oscillates with a period of 8 cycles per second. Okay, what does that mean? So let's rewrite this. This is a lot. So we have, at this point for our system, it's going to decay like e to the minus b over 2t. And this is assuming that b is between 0 and square root of 20. We have 1/2 times the square root of 20 minus b squared times the period equals 2 pi. We want 8 oscillations per second. That means that each second we have 8 oscillations. So the period is going to be 1/8 of a second. And the question is what is b? So plugging that back into this expression, my goal is to calculate the value of b. Let's see, so I can multiply both sides by 16. So I get 32 pi. I'm going to square both sides. Let's see, I can add b squared to both sides and subtract 32 pi squared. And I immediately see this is a problem. Notice this thing on the left-hand side is going to be negative. So that means it is not possible to design a system in this form that's going to meet my design objectives. Okay? So, what's important? What's important is, given a system like this and you're asked to design things, you have to be able to go through and recognize under what circumstances do you get oscillations, do you not get oscillations, and go through and figure out what's happening there. Be able to do the algebra to work with these complex numbers in a sane and consistent way. Recognize the meaning of this, but notice that in this particular problem, it's very important to know what's the regime of where you're going to get oscillations. And you need to be able to recognize when you get down to the end whether or not your answer makes any sense. Okay. So these can be tricky problems and there's a lot to keep track of. Let's do one last example. Okay, so in this example, let's determine a value of k so that we get 4 oscillations every 10 seconds. And we're going to assume that 0 equals 5n squared plus 2n plus k. In the future, you're going to have to be able to figure out this on your own. But for now, I'm trying to give you an idea of what you're going to be working with, and this is just one part of a bigger problem. So we're going to use the quadratic equation. B is 2. So then I'm going to get 2 squared minus 4. A is 5 in this case, so be careful. C is k over 2a. So let's clean that up. So this becomes 4 minus 20k over 10. I I know in advance that I want oscillations. So that means I'm going to break this up into two pieces. My real part and the imaginary part. I know in advance that it's going to be an imaginary part. So I want 4 minus 20k to be negative. So that means k has to be bigger than 4/20ths, which is 1/5. Okay, so that's going to be my check at the end. So because 4 minus 20k is negative, I'm going to write 2/10 is 1/5. I'm going to factor out a negative. So now I've got minus 4 plus 20k. And I know that 20k minus 4 is positive, so I can work with that square root of negative 1. So this becomes 1/10 times I times the square root of 20k minus 4. And my omega is 1/10 times the square root of 20k minus 4. So now what are the periods? So I have 4 oscillations per 10 seconds. So that means in 10 seconds, I've gone through 4 whole cycles. So each cycle takes 5/2 of a second. So my period is 5/2. So my period times omega. And so my period is 5/2. That has to be 2 pi. And now I want to solve for k, knowing that I know that k has to be bigger than 1/5. So let's see, this 5/10 becomes 1/2. This becomes, 1/4. So square root of 20k minus 4 times 1/4 equals 2 pi. Square root of 20k minus 4 is going to be 8 pi. I multiply both sides by 4. I'm going to square both sides. Add 4. And divide by 20. And notice this is 1/5 by itself plus this. So this is greater than 1/5. And so now this time everything works and it's fine. And if I use a value of k equal to that, that should give me my design objective of having 4 oscillations every 10 seconds.